the relation between the tangential velocity and the angular velocity. Let us consider a particle performs a circular motion along the circumference of a circle of radius r with constant angular velocity. Let a is the initial position of the particle. In a small interval of a time t, let the particle displaces to a new position b. The radius vector at point A is vector r1, radius vector at point B is vector r2. The angular displacement of the particle in time delta t is equal to del theta. The angular velocity omega is equal to limit delta t tends to 0 del theta by del t. When the particle moves from A to B, the linear displacement of the particle is along the arc AB, and if delta t tends to 0, arc AB is equal to line segment AB. It is represented by delta S. Now, angle is equal to arc upon radius. The angular displacement del theta is equal to arc delta S upon radius r. Therefore, delta S is equal to r into del theta. Therefore, limit delta t tends to 0. Del S by del t is equal to limit delta t tends to 0 r del theta by del t. The radius of the circular path is a constant, and what remains is limit delta t tends to 0 del theta by del t, and it is given by d theta by dt. ds by dt is the linear velocity and r constant, d theta by dt is the angular velocity. Therefore, v is equal to r omega is the relation between linear velocity and angular velocity. In vector form, vector v is equal to vector omega cross vector r.